For those of you that don't know, the archive is where most of the papers in our field get posted, and the archive, and all the papers have an archive number, and the archive number of this paper is, or these notes is 1, 2, and it's by so that's for most of the stuff on the symmetries. Okay, let me stop this recording. So let's begin. So last time we went through many details of the Maxwell theory. In particular, we finished up in writing the Lagrangian for the Maxwell theory, studied some of its properties, and discussed solutions, where we were looking at solutions in the so-called Coulomb gauge, where the divergence of the gauge field is fixed to be 0. And in that gauge, the equations just become Klein-Gordon equations for the individual components of the gauge field in the presence of some source term, which is just given by the current. And that means that the free particle solutions are given as plane waves, together with some coefficients, which are epsilon mu, and that's called the polarization vector. I emphasize at the bottom that the fact that the photon has a 0 mass is actually a prediction of the theory and is a consequence of gauge symmetry. Although we didn't explore this point in much detail, this will be discussed in much more detail in the QFT course of Giovanni. And just to elaborate a bit, the gauge condition that we're using tells you that the polarization vector contracted with the momentum is 0, and that leads to the 2 independent polarizations of the photon, which corresponds to the 2 helicity states that we saw must be there in the representation theory of the Poincaré group. Okay, so going back to the Poincaré group, now that we've got more experience with Lagrangians and symmetries and Noether's theorem, we want to work out the Noether currents for the Poincaré group. So if we have a Lagrangian that has Poincaré invariance, which is the case for most of the Lagrangians that you will work with this year, then for every generator of the Poincare group, there will be a conserved current according to Noether's theorem. So let's work out, first of all, how the field transforms, a scalar field, let's say, how a scalar field transforms under the Poincare group. Well, we have this formula here, which if we write it in terms of x prime, sorry, if we write x prime in terms of x, then x prime is given as the inverse of the transformation. We just invert this transformation and we get the right-hand side of the formula below. And explicitly, if we expand that out in terms of the generators, this gives us the these terms here. Now, if phi were transforming in a non-trivial representation of the Lorentz group, so if we were considering, for example, the Maxwell field or fields transforming in, say, the spinor representation, or it doesn't matter, then we would also get these terms here. Let me write this in a better way. So yeah, so the compact way of saying that will be if phi has non-zero spin. So just to make the formulas as compact as possible, I've suppressed any Lorentz indices that phi may have in these formulas. So remember here, D is the D of little m mu nu is the Lie algebra generator corresponding to m mu nu for whatever representation phi transforms as. And then these terms at the bottom come from the transformation of x itself. So, in other words, this formula at the bottom is the general formula for how a field transforms under Poincare transformations. So then, to compute the current, Noether's theorem is all about just computing dl by the partial derivative of L with respect to d mu phi. As we have done in our more simple examples. And so we compute that, then remove the parameters. If you remember that way back here, in the derivation of the current, the parameter drops out, the parameter alpha. In this case, we had one parameter alpha. The parameter drops out, and you're left with the derivative of the Lagrangian with respect to d mu phi times the variation of the field without the parameter. So that's true in general. So that's something that we already know. But another point is that the Lagrangian itself is a Lorentz scalar, so it will get a contribution from the Lorentz transformation, from the Poincare transformations of the coordinate dependence. So if you look in the transformation of phi, you have the piece here which you get if phi has a non-zero spin. So in other words, if phi transforms in a non-trivial representation, we get this term coming from the whatever representation phi is transforming in, and then we get this other term at the bottom coming from the fact that the coordinates have been transformed. So if phi was a scalar, then the D matrices there would be 0, and that term would not be there, but you would still get the second line. Well, the same is true for the Lagrangian, because the Lagrangian is a scalar itself. So the Lagrangian will have a term, will have a transformation coming from the corresponding to the second line. So we have to take that into account. And so that's what I've written here. And you can rewrite that in a more covariant form, if you like, or a more useful form, as I've done in the second line. So if we now take the different types of contribution, let's consider translations first. X goes to x plus a. Well, you see the term in the Lagrangian variation proportional to a is just delta mu nu times d mu L. So that's what I've written here. And then we get the contribution from the field variation here. And that, if we just go back and look at our formula, that's exactly the term proportional to a mu in the second line of the formula. So we get a tensor called T mu nu from this calculation, which it has two indices because you have the index for the transformation, which is mu. So in this formula is nu, and you have the index for the current itself, the fact that the current is a 4 vector, which is coming from the d mu phi in the variation of the Lagrangian. So we can just think of this as for every translation, you have a 4 vector. And we can take all of these four vectors, take the time component and integrate over space, and we'll get a conserved quantity. So if we just consider the four quantities t0 nu, then their integrals over all of space are conserved. And what are these quantities? Well, actually, these quantities are the energy and momentum of the field itself. Well, of the field theory itself, in a sense. So T00, the integral of that is actually the energy, and T00 itself is the Hamiltonian density. So we discussed the Lagrangian density, but we can also formulate the field theory in terms of a Hamiltonian formulation, and T00 is the Hamiltonian of the field theory. Oh, I've said that here, sorry. T0I, on the other hand, is the 3 momentum of the field theory. So that's why we call this thing the energy momentum tensor. And what we've shown here is that in any field theory, this formula gives you this set of conserved quantities, and you can compute this energy momentum tensor for any field theory. So, for example, if you, just to get a bit more of an idea of what we're talking about here, we've talked about the free particle solutions, but in general, the field theory, maybe I should start a new slide for this. Thus far, we've mostly discussed free fields. So free fields are very useful because you need them to set up the entire formalism of quantum field theory. But ultimately, one has to discuss interacting field theories, because free field theories, in some sense, physically are without content. So, e.g., we had, for example, the complex scalar field. We can make this theory interacting by adding a potential, for example. So in other words, we'll shift L by V of phi and phi bar. Sorry. And then, the equations of motion would become an equation like this, and also plus the complex conjugate equation. So you see that dV by d phi star becomes a source term for the Klein-Gordon equation. So instead of Klein-Gordon operator on phi equals 0, we now have something non-zero on the right-hand side, which we can think of as a source term. This is analogous to what we were just discussing with the Maxwell equations in the presence of a source. It's just that the current in scalar field theory it doesn't have a Lorentz label. I mean, sorry, the source in scalar field theory doesn't have a Lorentz label. The current, of course, does. So now, I haven't told you what this V of phi is. It could be some complicated function, and this system could admit solutions which describe other types of physics that go beyond the free particle solutions that we discussed before. So and once I add more fields, gauge fields and spinor fields that we will hopefully discuss soon, you get complicated systems of equations, or complicated looking systems of equations, and they admit solutions which have other physical interpretations. So there are solutions that correspond to like localized excitations, or sort of localized field configurations that have dynamics themselves. And even though I'm not going to go into any details about these types of solutions, if you compute the integral of t00 in such a background describing in such a solution, so t00 is literally just some functional of phi and d mu phi, but now it would involve the potential as well. You compute what that is, integrate it over all of space for your given field configuration, and this will tell you the energy of that field configuration. So that's another application of this conservation law. And knowing the energy, then you can go on to discuss the dynamics of such configurations. Okay, so that T mu nu is what you get from the fact that translations are a symmetry. So there's a lot of, I'm going to pause a second, there's a lot of noise outside, I can't hear. Seems to be going away, good. So that's what we get from translations, but we also have rotations and boosts. And so for every generator, m rho sigma, in our representation D, so for every rho and sigma, we get a 4 vector. And the first line is what we get from the fact that phi is a field that carries spin, according to the representation theory of the Lorentz group that we have studied in quite some detail. And then we get a contribution due to the fact that the Lagrangian itself is a scalar. And that contribution turns out to be kind of governed by the energy momentum tensor itself. So if we take the time component of these currents, we get these conserved quantities here, one for every Lorentz generator. And yeah, sometimes it's useful to think of the two terms, the two lines here in terms of sort of spin angular momentum and orbital angular momentum. But I'm not going to go into more detail on that. Now, what you will learn in the quantum theory is that these conserved charges, when we think of them in terms of, first of all, one can write down a formal expression for them in terms of the fields. Once one has that formal expression, in the quantum theory, the fields become operators acting on Hilbert space. And these conserved charges then become, you can think of them as operators on the Hilbert space, and as operators, they obey the algebra, the Lie algebra of the symmetry group that we started with. So in other words, the Hilbert space becomes a representation of the symmetry group of the theory. The Hilbert space, which we can think of in terms as a sort of function space. Okay, so this is just some additional motivation for why this has been introduced, and you'll see that more in the when you go on to study quantum field theory. So, as an exercise, I'd like you to just take the free complex scalar of a non-zero mass and write down, explain what is the full global symmetry group of this Lagrangian, and then compute all of the Noether currents for all of those symmetries, just so that you get used to seeing what these generators look like for Lagrangian theories. Okay, before I go on, are there any questions? Okay, so we're going to go on now to discuss just a few more points about global symmetries. So far today, we've mostly talked about Poincare, but now we want to consider further symmetries, like sometimes called internal symmetries, so non-space-time symmetries. So let's consider a Lagrangian now that has not just one, but n complex scalars. So you've got phi 1, phi 2, phi 3, all the way up to phi n. So each of these is individually a complex scalar. So I'm going to write this a bit better, it's not very neat. And I'm going to take the Lagrangian. So for each of those phi's, I could have written down this Lagrangian. And what I'm going to do is just take that Lagrangian, but now I've got n scalar fields and their complex conjugates. So I'm just going to sum all of those. So the sum is from 1 to n. So you see that this is, it's just d mu phi 1 star times d mu phi 1 plus the same thing for phi 2 and phi 3, etc. And a compact way of writing it I've introduced here the dagger symbol. I should probably add one more line here just for clarification. So this is plus dot dot dot. So I can write this actually the whole thing as d mu phi dagger dot d mu phi, where now I'm thinking of the phi a as a vector. I'm just using that notation because I can't think of a better notation. So d mu phi dagger is a row vector whose entries are, well, let me elaborate that in a second. Then the mass term that I've chosen is that all of the fields have the same mass. And the reason that this notation is useful should become elaborate, should become clearer in a while. But let me just emphasize that this is a row vector with entries like so. And then the d mu phi, sorry, with upper index is a column vector. And minus an appropriate thing for the mass term as well. Okay. So now we want to consider the transformation phi goes to m times phi, where m is an n by n matrix. And it's a complex matrix because phi is complex. So that means we also have to consider the transformation of phi dagger. Well, phi dagger is the Hermitian conjugate of phi, so it transforms to phi dagger m dagger. So if we look at our Lagrangian and how it transforms, since we're assuming that m is just a matrix, is a constant matrix, it doesn't depend on x and t. So d mu phi transforms in the same way that phi transforms. Let me make that clear. So L prime is the transformation of L. And so what we get is this transformed Lagrangian here. So if we now demand that the Lagrangian that we started with is actually invariant under this symmetry, it tells us that M dagger times M should be the identity matrix. And that's a symmetry group that we've met before. So the statement is that L prime is equal to L for the L that we wrote down, if and only if M dagger M is the identity. And that means that M is a unitary matrix. So for any unitary matrix, you would have this symmetry of this particular Lagrangian. And so our L would has the full UN global symmetry group, which from the point of view of Lie algebras, if we think of M as the exponential of a matrix, and I've written the matrix as I times U, then U dagger is equal to U, which means that U is a Hermitian matrix. Which means that we can write it, in the same way that we've written Lie algebra generators before, as a linear combination of some chosen basis Tm of the basis. You pick a basis for all Hermitian matrices, and you can write U as a real linear combination of those matrices, and there are n squared such matrices. So that's why this sum goes up to n squared. So for that Lagrangian, we can then compute the Noether currents just using Noether's theorem, and the answer that you get is linear in the generators of the transformation. This is an M here, not a mu. So for each of the n squared generators, we get a Noether current, which is conserved. And you see that the formula is very similar to the U1 case. So the U1 case has T is equal to 1. And then this would be the current for the U1 symmetry. The way that previous formula gets generalized is by having the Lie algebra generators appearing in the formula. So just to make this even more explicit, there's a nice exercise here, which is to work it all out in gory detail for n equals 2. So the first part of the exercise is to show that the Pauli matrices plus the identity matrix gives a basis for all Hermitian 2x2 matrices. So you see there are 4 matrices there because n squared is equal to 4 in this case. And then compute explicitly as a function of the fields. So in this case, we've just got 2 fields, 2 complex fields, phi1 and phi2. And I want you to write down the 4 conserved currents explicitly, so you get a good feeling for working with these types of functions of fields and so on. Any questions before we break? All right, so let's take the usual 10 minutes. It says 44 on my screen here. Pause. Sorry, I was locked out of the building somehow. Now I'm slightly out of breath. Okay. Right, so we're now going to move on to another important topic, which is related to what are called propagators, which classically arise from what are called Green's functions. And these are important to discuss how interactions, how signals propagate, how interactions propagate between particles. But here, we're going to be doing it at the field, at the level of the fields. So if we look at the Klein-Gordon or the Maxwell equations in the presence of matter, then we will have these source terms that we're now familiar with. And we want to think about solutions of these equations. How does one solve these equations? Well, the solutions are what can be obtained using Green's functions, named after the mathematician Green. And the point is that we're now going to consider functions of differences between space-time points. So x minus x prime is just a shorthand for x mu minus x mu prime. And the point is that if we're considering, say, the Klein-Gordon operator for zero mass, so everything I'm doing today here on will be just for zero mass, but one can easily include the mass term as well. I'm just dropping it for simplicity. Then if the Green's function obeys essentially the equation, but with a delta function source, so D4, delta 4 is the Dirac delta function, which means it's 0 if x is not equal to x prime, and it's infinity if x is equal to x prime. So the statement is that if d mu of g is equal to delta, then the general solution of the equation is given here. Namely, you have a term which is phi 0 of x, and phi 0 satisfies the free particle equation. And the second term, which is the integral over the points x prime over all of space-time of g times the source evaluated at x prime. Okay, so this is the standard way of solving these types of equations mathematically. Now, actually, it's true that if you give appropriate boundary conditions, because this is a differential equation that we're talking about, if we specify appropriate boundary conditions, then the actual solutions will be unique. Now, physically, what's going on here is that this Green's function has the physical interpretation as the field at x mu due to the source at x mu prime. Okay, that's why this G will actually be called a propagator. So it propagates the effects of the source at x prime to the space-time point of interest, which is x. So let's see this in more detail. And the way we do it is by introducing the Fourier transform of the Green's function. So this is the standard formula for the Fourier transform of a function. So we're now transforming from coordinate space x and t into momentum space, which and k is our momentum 4 vector. And I remind you that the Fourier transform of the delta function, or the delta function written in its momentum space representation, is given here. It's just the Fourier transform of e to the minus I k dot x, which means that the actual Fourier transform of the delta function is just 1. So let's operate with d mu on the Fourier transform of G. And our equation is saying that that this operation produces 1, because on the right-hand side of our equation we have the delta function. But we already know that how what d mu is in momentum space. It's just I times p mu, or in this case k mu. So we get minus k squared entering the integral under the integral sign. And then that has to equal the Fourier transform of the delta function. So in other words, this means that this means that the momentum space representation of the Green's function is just minus 1 over k squared. So we have this result here. And if we then substitute that into the general solution, it looks like this. Now, just to set things up, I'm going to give one of the most important examples of this. Let's consider a gauge field whose time components are 0, whose space components are 0, and whose time component is I'll just call it phi. So then we want to solve the equation box squared of phi is equal to rho, which is the density. And now I want to consider solutions in which phi itself is time independent. So we get the equation minus nabla squared phi is equal to rho, which is called the Poisson equation. So in this case, with the corresponding Green's function for this system is this three-dimensional Green's function, where you see I've got the three vectors now, because the time dependence has completely dropped out. And then we use spherical polar coordinates. So I'm going to actually, well, we're going to do this integral. So we use spherical polar coordinates to rewrite the d3k measure, and that becomes k dot k d of the magnitude of the vector times sine theta d phi. And let's now say that, imagine we're starting at the origin, if x prime is the origin, and we're looking at propagation out to some distance r. We can use the fact that k dot r is then the magnitude of k times the magnitude of r times cosine of theta. So our integral then becomes the integral of dk times e to the I kr cosine theta, whole thing multiplied by sine theta, d theta, and d phi. And because we have a k squared in the measure here, it cancels out the k squared in the denominator of the Green's function. And this integral turns out to be given by 1 over 4 pi r, or 1 over 4 pi times the magnitude of r. Where we're using the following two identities. So have I done that in one step or two steps? Yeah, so I did it in two steps. So if you use these two identities, we get this following result, okay? Now, 1 over 4 pi r is the potential, is the electrostatic potential for a point source. It's the Coulomb potential. And from that, one can get the general solution for static electromagnetic field configurations from the previous formula. So we've derived the 1 over r potential due to a point charge, and that also means that if we just take the derivative of the potential, we'll get the force. So this is actually a derivation of the 1 over r squared force law of electromagnetism. And the fact that it was the massless Klein-Gordon operator appearing means that for any situation in which you've got massless Lorentz invariant equations for massless Lorentz invariant theories, you will always get a 1 over r squared force law, or equivalently a 1 over r potential. So that's even true for gravity, where even though we haven't seen gravitons, and probably never will see gravitons, the field corresponding to the graviton is a massless field in a Lorentz invariant theory, and that's why gravity has a 1 over r squared force law. Maybe I should write that at the bottom. So this is actually a really sort of fundamental result of classical field theory, and really demonstrates that the Green's function describes the propagation describes the change in the field due to a source, and we interpret it as a signal propagating from the source to the point of interest. Okay, so now we're going to return to the general case where we've got time dependence. Oh, sorry, before I do that, I forgot, this is in 3+1 dimensions. If I was in d dimensions, if I was in d+1 dimensions, then the force law would be like 1 over r to the d-1. Okay, so what I've done here is written the formula we had before for the Green's function, but I've separated out the spatial momentum, the d3k, from the dk0. And what we want to do is to actually do this k0 integral. So the way we're going to do it is, so you know, the k0 integral is a real integral, but we'll use complex analysis and Cauchy's theorem to do the integral, which means we have to take, we'll treat k0 as complex, so we analytically continue to the complex plane, complex k0 plane, and choose a contour, contours around which we will integrate, and the contours have to include the real k-axis, which is the actual integral we want to do. In other words, we choose contours along the real k-axis, which then, when you close them, however you close them, you get a 0 contribution from the rest of the contour. Now, the important point is that we have 2 poles in this integral at plus or minus the square root of k squared. and the poles are the most important feature that gives rise to the results. Now, we can choose the contours in different ways, and depending on which contour we pick, we'll get different solutions. And the reason for that is, if you look at the integrand, we have this e to the minus I k0 times x0 minus x0 prime. In order to apply a Cauchy's theorem, we want there to be a zero contribution from infinity, which means that if we go up and down the imaginary k0 axis, we need to get 0 at infinity, and that in turn depends on the sign of x0 minus x0 prime. That's very interesting, because if x0 is bigger than x0 prime, it means that the signal originated in the past. Whereas if x0 is less than x0 prime, it means that the signal originated in the future. So this, doing this integral, computing tells us that this Green's function has got something to do with causality as well. All right, so let's pick this contour, which is given by the green line. And let's consider first the case when x0 is bigger than x0 prime. So if I close that contour above 0, so I make the loop in the positive imaginary direction and close it, I get no contribution at all. I get 0 because the contour does not include the poles. If I close it below 0, then I pick up both of the poles, which means that we have to introduce the step function, which enforces the fact that we get sorry, I've done this the wrong way around. Am I? Well, let's go back to our integrals so we can fix it. So this is the quantity that fixes whether or not we get non-zero contributions depending on the sign. So if we consider the contour closing in the plus I direction, we get 0. But in the plus I direction, you see, if I consider k0 being a positive number times I will get e to the, I would get e to whatever that number is, but that number is positive. But the integral has to go to 0 sufficiently fast, which means that x0 minus x0 prime must be negative. And it's vice versa for closing the contour in the opposite direction. So yeah, this was actually right. So now if we just apply Cauchy's theorem, we get two contributions from those two poles, which are given here, where K is the absolute value of the 3 momentum, which is where the poles, plus and minus that is where the poles are. So we get these two contributions. To do that, slightly, just to elaborate that, to do it explicitly, one uses this identity. And for that choice, we see that the only contribution comes from the negative imaginary axis. Now, this contour gives what's called the retarded propagator, because x prime is in the past of x. So that's why it's called retarded. And one can compute, one can get an even, one can do the momentum integral, the K integral as well, by doing the same change to spherical polar coordinates, and picking up the two contributions due to the poles, as we just did, and multiplying by the step function. If you put all of these together, you can convince yourself that using the same integral that we used before, where was it? For the static case, using this same identity at the top, that we get this expression with the star here, which is just 1 over the potential, again, 1 over 4 pi times the potential, times the step function, times the sum of these two delta functions. So, you get these two delta functions because you get the delta function because this combines with these two phases. But since we're in a situation, well, since the distance is always positive, the second delta function doesn't contribute, and we end up with this formula here. So, as I said before, this Green's function is called the retarded propagator because the time that the signal is emitted is before the time x0. And in fact, in this case, because we're dealing with the massless equation, the massless wave equation, the signal is traveling at the speed of light. And that's because of this delta function here. And you can convince yourself that that delta function is Lorentz invariant. You can actually write it in this way, but that's just as an aside. So if we think of, if we draw a light cone whose origin is the point x mu, then in terms of in a sort of space-time diagram, the point x prime mu is actually on the light cone because the signal is traveling at the speed of light, and it's in the past light cone of the point x mu. Everything that I've said can be repeated by for the massive case by just shifting k mu squared to k mu squared minus m squared, and then the point x prime would be inside the backward light cone, because propagation via particles that have a non-zero mass is below the speed of light. It takes place below the speed of light. Now, we could do the same exercise closing the contour underneath the poles instead, and then we'll only get contributions from the future light cone. And instead of having the delta function with a plus sign between the two terms, we get the delta function with a minus, sorry, instead of having delta function with a minus sign between the time and space components, we get a delta function with a plus sign. And this is called the advanced propagator. And in quantum field theory, once you you'll rederive these formulae in quantum field theory. The retarded propagator has the interpretation of propagating particles from x prime to x, whereas the advanced propagator describes propagation of antiparticles. And that's also related to our interpretation of the negative energy solutions of the Klein-Gordon equation, or in fact any relativistic equation, as antiparticles. Yeah, I think that's a good place to stop for now. We will. Oh, I forgot to start the recording when we came back from the break. But anyway, I think it's being recorded on Zoom. Apologies about that. It's because I was rushing back. Yeah, before we go on with this, we'll go on with this next time. I think this is a pretty good place to stop. There are two other, just to flash forwards, one can also consider these two contours here And these give you what's called the Feynman propagator. Which sort of combines the particles and antiparticle propagation in an elegant way. That's the interpretation. We should discuss homeworks. And also, I wanted to give you a reference for this. So, let me write it down here somewhere. So that's this book here by Barut. And yeah, so the stuff on propagators is from chapter 4, section 4. And this is the first edition. This, I don't know if this book has been, I didn't check if it's been revised or. Well, this is from the Dover edition of the book, which is the publisher. So I think there was an earlier version of it, and it's Barut, A. Barut. These propagators get I mean, you'll derive them in different ways in field theory as well as more general forms of Green's functions. So exercises. Can someone remind me what page we were up to as far as exercises were concerned? Where did we stop the exercises last time?
Last time we stopped at page 28, but then you said for this week we have to do till 90, I guess.
Oh, I've already said up to page 90. Okay.
Mm-hmm.
Okay, that's fine then. Let's see if I want to revise that. No, that's okay. I'll set more on Tuesday then. Okay, I think that's all for today then, and we'll meet again on Tuesday. Oh, but I didn't actually ask, does anyone have any questions? Sorry.
Sure, about the conserved current corresponding to the Lorentz transformation. So how can we interpret it? I mean, just like the case of the energy momentum, so we take the 0, elements and we integrate and we obtain.
Yeah, so I was trying to emphasize that doesn't matter what the symmetry is, the answer you get from computing this quantity, the conserved quantity, like the zero component of the whatever conserved quantity it is, in the end gets interpreted as an operator which implements that symmetry on the Hilbert space of the theory. So it means that all the states of the theory form a representation of the symmetry group in the quantum theory. Simply that.
Yeah, and I asked about the case of the charge of the Lorentz corresponding to the Lorentz transformation, Lorentz symmetry. So we obtain a tensor with 3 indexes, and how can we interpret it as a physical quantity?
So it's not a physical quantity. The conserved quantity is a field operator which implements the symmetry on the Hilbert space. So it just means that states have to form, it means that the physical states form representations of the symmetry.
Okay, I'll think about it. Thank you.
And it means that the physical spectrum is constrained by the fact that you have to have these representations.
Can you elaborate on that? How do you mean by constrained because of the symmetry?
Well, what I mean is that if the symmetry wasn't there, the spectrum could be much more complicated. Take, for example, the spectrum of the Hamiltonian. So if you're able to solve, if you're able to solve a quantum field theory, it means that you can specify all of the eigenmodes of the Hamiltonian operator. So that would be T00. And all of those, the solution of that problem would be a representation of the full symmetry group that you started with. Does that make sense?
Not quite clear to me.
Okay, maybe I can try and think of a more concrete example, and I'll show you next time.
Yeah, thank you.
Any other questions? All right. So see you next week. Have a nice weekend, if I don't see you before that. And I'll send this version of the notes